June 12, 1943, Burbank, California. Lockheed Aircraft Corporation. Building 304. The afternoon sun cuts through the industrial haze, casting long shadows across the concrete apron where P-38 Lightnings sit in diagnostic rows. The air tastes of aviation fuel and hot aluminum, that metallic bite that clings to the back of the throat. Inside Hangar 7, the temperature hovers near 90 degrees despite the open bay doors. A single aircraft dominates the space, a P-38J with its cowlings removed. Twin Allison V-1710 engines exposed, like the dissected organs of some chrome-plated predator. Around it, men in oil-stained coveralls and rolled shirt sleeves stand in a loose semicircle, their faces etched with fatigue and frustration. They are engineers, mechanics, military liaisons. They have been staring at this problem for months, running tests and calculations, and they are no closer to an answer than when they began. Beneath the port engine nacelle, a single man kneels. He is perhaps 50 years old, gray threading through dark hair, wire-rimmed glasses smudged with fingerprints. His name is not Kelsey or Johnson or any of the celebrated engineers whose names would later fill the history books. He is Anthony Rossi, a civilian machinist, a tool and die maker pulled from the Ford plants in Detroit because Lockheed needed hands that understood metal under stress, men who knew the language of bolts and tolerances and the thousand small ways that machinery betrays itself. In his calloused hand, he turns a single bolt. It is perhaps 3 inches long, unremarkable, the kind of hardware that exists in the thousands throughout any aircraft. And yet Rossi stares at it as though it contains a secret. Because it does. The problem consuming Lockheed, the Army Air Forces, and every P-38 pilot flying missions over Europe is this: the Lightning is dying in ways that make no tactical sense. Not from German guns, though those claim their share, but from itself. Engines seizing at altitude, compressor failures that send aircraft into uncontrollable spins, fires that erupt without warning in the engine nacelles, burning so intensely that pilots have less than 30 seconds to bail out before the cockpit becomes an inferno. The loss rate is approaching 15% per month, and no one can explain it. The P-38 was supposed to be untouchable. Instead, it is disintegrating. The P-38 Lightning was born from a 1937 Army Air Corps specification that seemed designed to be impossible. An interceptor capable of 360 miles per hour at altitude, able to climb to 20,000 feet in 6 minutes, with endurance enough to patrol for an hour at full military power. No existing aircraft came close. Lockheed's answer was radical. A twin-engine, twin-boom configuration with the pilot housed in a central nacelle, tricycle landing gear, and all armament concentrated in the nose. 120mm cannon and 450 caliber machine guns, firing through the propeller arc without synchronization, delivering a weight of fire that could saw a bomber in half. The prototype XP-38 flew in January 1939 and shattered every expectation. It was fast, maneuverable, and spectacularly modern in appearance. The Army ordered it into production immediately. By December 1941, when Pearl Harbor thrust America into war, the P-38 was already operational, the most advanced fighter in the American inventory. It dominated in the Pacific, where its range and twin-engine reliability made it ideal for overwater missions. It became the mount of America's top aces. Richard Bong flew it. Tommy Maguire flew it. It was the aircraft that shot down Admiral Yamamoto. But Europe was different. Europe demanded something the P-38 had never been fully tested for: sustained operations at extreme altitude in sub-zero temperatures. The strategic bombing campaign required fighter escorts that could accompany B-17s and B-24s to targets deep inside Germany, missions that took place above 25,000 feet, in air thin enough to starve engines, in cold that could freeze hydraulic fluid and shatter perspex canopies. The P-38 had been designed for coastal defense and interception, for short, violent engagements at moderate altitude. It was being asked to fly 4-hour missions in conditions that would have grounded any aircraft in the pre-war world. And it was failing. By the spring of 1943, P-38 groups stationed in England were reporting engine malfunctions at rates that exceeded combat losses. 8th Air Force commanders began quietly questioning whether the Lightning was suitable for the European theater. Some suggested reassigning the P-38s to the Mediterranean or the Pacific. Others advocated switching entirely to single-engine types, P-47 Thunderbolts, or the new P-51 Mustangs. But the P-38 possessed capabilities no other American fighter could match. The range to escort bombers to Berlin and back, the firepower to destroy German fighters in a single burst, and the redundancy of twin engines, which meant a pilot could limp home on one power plant. Losing the P-38 would mean losing the ability to protect bombers over the deepest targets. It would mean watching the bomber offensive bleed to death over Germany. Lockheed dispatched engineering teams to England in April 1943. They interviewed pilots, examined wreckage, pulled engines from damaged aircraft, and subjected them to ground testing. The engines ran fine on test stands. The turbochargers functioned within specifications. The fuel system showed no contamination. Yet in the air, over Germany, the aircraft continued to fail. Pilots described the same sequence: a slight hesitation in throttle response at high altitude, followed by a compressor stall, then either an engine fire or complete seizure. The failures were not random. They clustered around specific flight profiles, always during sustained high-power operations above 24,000 feet. German pilots noticed before the Americans understood. Luftwaffe intelligence reports from mid-1943 contain references to the Gabelschwanzteufel, the fork-tailed devil, and its peculiar vulnerability. German fighter tactics evolved to exploit it, rather than engage P-38s in turning fights, where the American aircraft's twin engines and heavy armament gave it overwhelming advantage. Luftwaffe pilots began using slashing vertical attacks, forcing the Lightnings into sustained climbs at full throttle. Then they would disengage in orbit, watching. Within minutes, often as not, the P-38's engines would fail on their own. Compressors stall. Fire. Seizure. The fork-tailed devil would drop from formation trailing black smoke, and the German pilot would not even expend ammunition for the kill. The Germans attributed this to inferior American engineering. Their intelligence assessments concluded that the P-38, for all its impressive performance on paper, was fundamentally flawed, crude, over-engineered, incapable of sustaining the rigors of high-altitude combat. This confirmed what they wanted to believe, that German technology, German precision, German discipline were superior. The Americans could produce aircraft in vast numbers, but they could not produce quality. The P-38's failures were proof, but American engineering culture operated on different principles. Where German design emphasized perfection at the prototype stage, getting it right the first time, American design emphasized iteration. Build it, test it, break it, understand why it broke, fix it, and test it again. Failure was not shameful. It was informative. And so when the P-38 began failing over Europe, Lockheed did not accept it as an inherent limitation. They hunted for the cause with methodical, relentless determination. Anthony Rossi was not part of the original engineering team. He was brought in later, when the investigation stalled, as part of a broader effort to involve manufacturing specialists in the diagnostic process. Rossi had spent 20 years at Ford, working in the tool and die shops where automotive engines were built. He understood machining tolerances, thermal expansion, the way metal behaved under vibration and stress. He was not an aeronautical engineer, and he did not think like one. Where engineers looked at systems and specifications, Rossi looked at the physical reality of how parts fit together. He was assigned to inspect P-38s that had been returned, from Europe for analysis. Damaged aircraft that had suffered engine failures but had managed to make it back to England, then been shipped stateside for detailed examination. The engineers were focused on the engines themselves, tearing down turbos, inspecting impeller blades, analyzing fuel flow. Rossi was supposed to assist, but his background drew his attention elsewhere. He looked at the installations, the mounts, the way the engines attached to the airframe, and he found something. In multiple aircraft, always in the same location, a specific bolt in the engine mount assembly showed unusual wear. Not failure, the bolt had not broken, but wear that suggested movement, vibration, stress cycling. He brought it to the attention of the lead engineers. They were polite but dismissive. The engine mounts were not the problem. The mounts were simple, robust, over-designed for the loads they would ever experience. A worn bolt was a curiosity, nothing more. But Rossi kept looking. He examined every returned P-38 he could access. 12 aircraft. 15. 20. And in every case, the same bolt showed the same wear pattern. He began to form a hypothesis, not from theory, but from experience. The engine mounts, he believed, were shifting under specific conditions. The combination of extreme cold, sustained vibration, and rapid thermal cycling that occurred during high-altitude combat. The shifts were tiny, measured in thousandths of an inch, but they were enough to misalign the engine relative to the airframe. And that misalignment placed stress on components that were never designed to bear it. Fuel lines, hydraulic lines, intercooler ducting, turbocharger linkages. The engine would run, but it would run wrong. And eventually, something critical would fail. It was an elegant theory, but it violated engineering orthodoxy. Engine failures were supposed to originate in the engines, not in the mounts, not in a bolt. Rossi proposed a test. Replace the standard mounting hardware with reinforced brackets and high-tensile bolts designed to maintain precise alignment under thermal stress. It was a trivial modification, adding perhaps 4 pounds to the aircraft. It would cost almost nothing. But it required admitting that the problem was not exotic or complex, but simple and embarrassing. A bolt. The engineers resisted. Rossi persisted. He was not eloquent or politically connected, but he was stubborn, and he had the advantage of being right. He convinced a sympathetic project manager to authorize a limited test. 3 P-38s were modified with the reinforced mounts and subjected to high-altitude flight testing over the Sierras, running full-throttle climbs to 30,000 feet in conditions that simulated combat. The engines performed flawlessly. No compressor stalls, no fires. The test pilots reported that throttle response was crisper, smoother than they had ever experienced in a Lightning. The results were undeniable. By July 1943, Lockheed had incorporated the reinforced mounts into production aircraft. Retrofit kits were rushed to Europe, and maintenance crews worked around the clock to modify aircraft already in service. Most pilots were never told the details of the fix. They simply noticed, over the course of weeks, that their engines stopped failing. The compressor stalls became rare. The fires almost vanished. The P-38, almost overnight, transformed from a troubled compromise into a reliable warhorse. The impact was immediate and measurable. In August 1943, the P-38 groups in England flew 11847 sorties with an engine-related abort rate of 4%, down from 21% in June. By September, the abort rate had dropped to 2%. Loss rates from mechanical failure fell by 70%. The fork-tailed Devil, once infamous for betraying its pilots, became one of the most dependable aircraft over Europe. And the combat results followed. P-38s began ranging deep into Germany with the confidence that had been missing. They escorted bombers to targets the Luftwaffe thought were unreachable. They engaged German fighters over Berlin, over the Ruhr, over Munich, and they came home. The psychological effect on Luftwaffe pilots was significant. The intelligence reports that had confidently predicted P-38 failures grew quiet, then stopped. The fork-tailed devil was no longer vulnerable. It was dangerous. The Bolt, Rossi's Bolt, though no one called it that, became a symbol among the ground crews. Mechanics who installed the retrofit kits knew they were saving lives. They worked with a sense of purpose that transcended routine maintenance. Each modified aircraft was one less pilot who would die from an engine fire. Each successful mission was proof that small things mattered, that attention to detail could change the course of battles. The Bolt itself was unremarkable, identical to thousands of others in supply depots across England. But in the right place, under the right conditions, it was the difference between life and death. The Germans never learned what had changed. They observed that the P-38s stopped failing, but they attributed it to factors beyond their understanding. Perhaps new engines, perhaps different fuel, perhaps simple luck. The idea that the fix was a bolt, a piece of hardware any machinist could fabricate, was beyond their conceptual framework. German engineering culture revered complexity and precision. Solutions were supposed to be sophisticated, the product of advanced theory and meticulous calculation. A bolt was crude. It was beneath consideration. And so they never sought the answer, never understood that the Americans had solved their problem not through genius, but through the unglamorous, essential work of paying attention to how things actually failed. This was the divide between the two engineering cultures. The Germans built aircraft that were marvels, the FW-190, the Me-262, machines of extraordinary performance and innovation. But they could not sustain them. They could not adapt quickly enough when flaws emerged. Their production system was artisanal, and their solutions were often complex redesigns that took months to implement. The Americans built aircraft that were good enough, and then they made them better, incrementally, relentlessly. A bolt here, a pump there, a redesigned cowling, 100 small fixes that compounded into overwhelming advantage. By the winter of 1944, the P-38 was escorting bombers to targets across Germany with loss rates lower than any other American fighter type. It was shooting down German aircraft at a ratio of 4-to-1. It was strafing airfields, destroying locomotives, dominating the air war in ways that seemed impossible a year earlier, and all of it traced back, in part, to a civilian machinist who had looked at a bolt and understood. There is a particular grace in solutions that are invisible. The pilots who flew P-38s in late 1943 and 1944 did not know about Rossi's bolt. They knew only that their aircraft had stopped failing, that they could push to full throttle in a climb and trust the engines to respond. They flew with confidence, and that confidence translated into aggressiveness in combat, into willingness to engage German fighters rather than avoid them, into the kind of air superiority that wins wars. Rossi himself did not receive recognition. There was no medal, no commendation. His name appears in no official histories of the P-38 program. He returned to Detroit after the war and resumed his career in the auto industry. He died in 1971, and his obituary made no mention of his contribution to the air war over Europe. But the pilots he saved, men who flew missions they might not have survived, who came home to families because their engines did not fail, carried his legacy whether they knew it or not. The bolt remains a symbol of a larger truth, that wars are won not only through brilliant strategy or superior technology, but through the accumulation of small advantages, each one insignificant on its own, but together creating a system that cannot be overcome. The Germans had superior fighters in 1944. The Me-262 jet was faster than anything the Allies flew, but they could not field them in sufficient numbers, could not train pilots fast enough, could not sustain operations because their logistics and production were strangled by bombing campaigns that American escorts like the P-38 made possible. In the decades after the war, historians documented the technologies that defined the conflict. They wrote of radar and code breaking, of the atomic bomb and mass production. The P-38. Lightning appeared in these accounts as a successful fighter, notable for its distinctive silhouette and long range. The engine problems were footnotes, if mentioned at all. The fix, a reinforced bolt, a modified mount, was too mundane to merit detailed discussion. But among veterans, the story persisted. In reunions and memoirs, P-38, 38 pilots spoke of the moment when the aircraft became reliable. They did not know the technical details, but they remembered the feeling. The relief of taking off without wondering if the engine would betray them. The confidence of engaging enemy fighters without holding back throttle. The simple, profound gratitude of coming home. Some of them, in their later years, wondered who had solved the problem. They imagined teams of brilliant engineers, complex redesigns, advanced technology. They never imagined a single man with a bolt in his hand. And perhaps that is fitting. The most important contributions in war are often the least celebrated. The unglamorous work of making systems function, of finding and fixing the small failures before they compound into catastrophe, of paying attention when others look away. Rossi's impossible trick was not impossible at all. It was simply the work of someone who cared enough to look closely, to trust experience over theory, to persist when others dismissed him. Here is the final truth that the bolt represents. Abundance is not only material, it is also intellectual. The Americans had the luxury of welcoming input from machinists and factory workers, from men who were not credentialed engineers, but who understood metal and stress and the practical reality of how things break. They had the cultural confidence to listen when someone like Rossi said, "I think it's this bolt." The Germans, for all their engineering brilliance, did not have that flexibility. Their system was hierarchical, credentialist, resistant to input from below. And so when their aircraft failed, they looked for complex answers and often missed the simple ones. The P-38 flew on, almost untouchable, not because it was perfect, but because someone made it reliable. One bolt, properly placed, held when it might have slipped. One civilian's persistent attention changed the trajectory of air combat over Europe. And tens of thousands of bomber crewmen, flying deep into Germany with lightning escorts overhead, lived because of work they never knew had been done. The bolt itself, if it still exists, sits in a storage depot somewhere, corroded and anonymous, but its legacy is written in mission logs and loss reports, and the letters that pilots sent home saying they had returned safely. It is written in the contrails that streaked across German skies, in the wreckage of Luftwaffe fighters that met P-38s and lost, in the quiet, unglamorous victories that accumulate into something called freedom. Rossi's trick was no trick at all. It was simply the willingness to see what others overlooked, to care about the small things, to understand that in war, as in life, everything depends on whether the bolt holds. And the bolt held.